Hello, this is Mrs. Taylor, and I'm going to introduce you to the first derivative test. The reason why this is important is because it allows us to find extrema without having to look at the graph. And so on page 181 in your textbook, you'll see this theorem. It's listed as 3.6, and it's the first derivative test. And it states, let C be a critical number of a function f that is continuous on an open interval I containing C. So all this is saying is let C be an x value on this interval where the derivative equals 0 is undefined. If f is differentiable on the interval, except possibly at C, then f of C can be classified as follows. If f prime of x changes from negative to positive at C, then f of C is a relative minimum of f. So if you think about it, if f prime of x changes from negative to positive, that's slope. So what this is saying is if it changes from a decrease to an increase, and that makes sense, that would make a minimum because it would be like the bottom of a U, decreased, increase. Number 2 says if f prime changes from positive to negative at C, then f of C is a relative maximum of f. So positive to negative change in slope would mean increase to decrease, which makes sense because that's like the top of a hill. That would make a maximum. And then if f prime does not change sign, then f of C is neither a maximum or a minimum. So if you look at our examples, the minimum here is decrease to increase, negative slope to positive slope. Maximum is positive slope to negative slope, or increase to decrease. And then the bottom two examples are examples of neither, because the one on the left is increasing the entire time, but you still have this horizontal tangent line at C, so that's why it's a critical value. And then this example on the right, this is decreasing the entire time. So it's not a maximum or a minimum, but you still have that horizontal tangent line, which creates a critical value. So let's apply this test to a problem. Find the extreme values of the function and where they occur. And our function is y equals 2x squared minus 8x plus 9. And the first derivative test is based on the first derivative, so that's what I have to find. And so the derivative of this function would be 4x minus 8. And in order to apply the first derivative test, we need the critical values, or critical numbers. And so I need to take my derivative, set it equal to 0, and solve. So I would rewrite the derivative as 0 equals 4x minus 8, add 8, divide by 4, and x equals 2. So my critical value is at x equals 2. Now, in addition to the first derivative test, I'm going to introduce you to sign charts. Sign charts are tools that allow us to interpret things about our derivatives more easily. So instead of trying to think through it all in our head, it creates a visual tool to better organize the information. Keep in mind that a sign chart is not support for an answer. So if the directions say justify your answer, you can't just have a sign chart. You have to actually interpret the sign chart in words. But because these directions don't say justify, then we'll save that for another video. So a sign chart is basically a number line where you are marking your critical values. And you need to label it whether it represents the first derivative or the second derivative or the function. This is the first derivative, so I put y prime right here. And then I need to mark my critical values, which I have 1, and x equals 2. And then what I do is I pick test points to the left and to the right of each critical value, and I evaluate the derivative at those test points. Because what that will do is communicate to me whether the derivative is positive or negative on that interval. And so to the left of 2, let's pick something easy, 0. So if I evaluate y prime of 0, excuse the handwriting, that would be negative 8. Now, in the end, it doesn't matter whether I know that it's negative 8. It just matters if I know if it's negative or positive. So instead of writing negative 8, I'm just going to mark it as negative. Because again, this is not justification. This is just a tool. So it can be written in any form that I need it to be for me to use it. Okay, so Now I know that from negative infinity to 2, this function is decreasing. And then pick a point to the right of 2, which would be 3. That would be a straightforward one. And when I plug that into the derivative, I get 12 minus 4, which would be a positive. And so from my sign chart, I can see easily that the function is also increasing from 2 to positive infinity. So if they ask me to determine the intervals of increase and decrease, I can do that using the sign chart. I can also determine extreme values based on the first derivative test because it's changing from negative to positive. And according to the first derivative test, that means that at x equals 2, I have a relative minimum. And so when it says and where they occur, they're asking you for the x value as well. So I can write that I have a relative minimum at x equals 2. And if they asked me to justify, I would just simply state relative minimum at x equals 2 because the derivative changes from negative to positive at x equals 2, or I could state that the function changes from decrease to increase at x equals 2. Either phrase would be an acceptable justification. And so that's how you apply the first derivative test, and that's how you use sign chart.